Welcome to a video on how to do absolute values, reciprocals, and roots of polynomial functions. So let's start off with how to do absolute value of a function first. So absolute value, you basically have to think about all the y values that are negative will become positive, and all the y values that were positive will remain positive by definition of what absolute value does to the graph. So let's do that. So this piece of the graph will remain the same. So it'll be invariant. Then this y value down here right now is very close to -3. So that implies absolute value of that would be very close to +3. So you're going to keep the x the same. So right above this point, you'll have a point close to where negative or +3 is. Then 0, absolute value of 0 stays 0, so that point stays where it is. And then our next turning point is y is very close to -2, so that means absolute value of that is +2. So keeping x the same, it's going to be somewhere over here. And then lastly, this part of the graph again stays the same because of absolute value of a positive stays positive. So we have to take all of these bottom portions and just reflect it up above. So I'll do that, and that would be our graph. This sharp point right here is called the cusp. All right, the next type we're going to talk about is how to do a reciprocal of a polynomial. So the key thing is to find or flip the y values, find the reciprocals of all the y values. When you do reciprocal of 0, however, you'd get something undefined, which we will show with a vertical asymptote. When you reciprocate 1, it stays 1. When you reciprocate -1, it stays at -1. So these points are called invariant points. So let's try that on the same polynomial. We're going to do a sketch of a reciprocal of it. So let's sketch the invariant points at 1 and -1. Okay, and then reciprocals of the zeros become vertical asymptotes. So there is no graph at these values of x. And then the turning points, this point right here, that was y equals close to -3. We do a reciprocal of that, we'd have -0.33333 repeated. So instead of this point here, you're actually going to plot it for the same x value, but close to 0 here. And same thing with this point, y equals -2 becomes -0.5. So it will be plotted for the same x value right here. You can, of course, do the reciprocals of every single y value that you see there, but that's infinitely many of them. So let's think about it in general, what's happening. So these y values tend to positive infinity. So as y goes to positive infinity, the reciprocal of it will go to 0. This little portion right here between 0 and 1 for the outputs, the y values are, if you're thinking about it going this way, y values are tending towards 0 from the positive side. So as y goes to 0 from positive side, the reciprocal of that will tend to positive infinity. Just think about dividing by really small numbers, you get really big numbers. So this portion of the graph turns out to be something like this. Another way of remembering things, if the graph is increasing, your graph will decrease. Okay, so in this portion right here, the original graph polynomial is decreasing and then increasing. So our graph will do the opposite. So it will increase first like this and then decrease afterwards. In terms of this notation, you could also think about it as y goes to 0 from the negative side. 1 over y will tend to negative infinity. So this portion of the blue graph goes to 0 from the negative side. So the reciprocal will go to negative infinity there. And this will also kind of be the same. And on this side, the same as well. Now I want to talk about some key things that you might want to remember for future reference. Just like with multiplicity with polynomials, with reciprocal, you could also notice some specific patterns for what happens near that vertical asymptote. So this at x equals -2, for example, the multiplicity is odd. So odd multiplicity would imply that these the behavior near this will be in opposite direction. So if this is up, this one's down. If the multiplicity is even, the behavior near the asymptote will be in the same direction. So over here at x equals 0, the asymptote here, both arms go in the same direction. And then this multiplicity here is odd, so arms go in opposite directions. Okay, so just key things to remember, just because it's easier to do that instead of, thinking about what it tends to instead. All right, we have one more type. How to do roots of polynomials. So you might want to just find key points and do roots of them, whether it's even root or odd root. You should know that root of 0 stays 0, root of 1 stays 1, and root of -1. If it's even root, it won't exist, but if it's odd root, it will stay the same. So these points will be invariant, except for even roots. There will be no graph for any negative outputs. Okay, so we're going to try an even root first. Okay, so I'll start by plotting the invariant points. So starting with 1 right here, square root of 1 stays 1. Square root of 0 stays 0. Square root of -1, we can't draw anything to do with negatives. And then this 0 stays the same. This graph will not be there. And then this square root of 0 stays 0, and square root of 1 stays 1. Okay, so we only have 1, 2, 3, 4, 5 invariant points here. The rest of it, you should just pick some values of a y value and do a square root of it. So for example, this right here is y is approximately 0.5. So when you do square root of 0.5, you get roughly 0.7. So it is actually higher than the y value that we have. So the bulge happens a little bit this way. And then if you take another value, let's say this one right here, y equals 3, and then do square root of 3, you'll have close to 1.7. So it is smaller than the given value. So 1.7 would be just slightly lower than 2. Notice you're keeping x values the same when you do that. So this will kind of go like this. Graphs would be turned that way. On this side, you can try some values as well. So for example, this one right here, that's the same thing as the 0.5 that we had before, so it would be higher than that, 0.7. Okay, and if we take this 3 here, this one, we would have 1.7, so somewhere here. Let's take another number, like somewhere really close to 0. Let's say 0.1, and you do square root of that. So square root of 0.1 is 0.3, so it's still really, really close to the x-axis. So this actually tends to curve this way. Later on, when we study concavity, this would be very clear. For now, it's kind of unclear exactly why it's turning that way, whereas this one was turning this way. All right, so now it's time to do an odd root, not an even root. So let's do cube root of the same polynomial. I'm going to start off again by doing the invariant points. So 1 and 0 and -1. This time -1's cube root of -1 stays -1. So I have all of these invariant points. And now we just need to do cube root of specific y values. Let's do this turning point right here. So y being close to -3. When we do a cube root of that, we get negative 1.4. So 1.4, -1.4 somewhere here. Okay. Let's do this one right here. Turning point at y equals -2. So cube root of -2 would be -1.3 roughly. So -1.3 is slightly lower here. Okay. And let's do, I don't know, this number here, 3. So we want to do cube root of 3, which is positive 1.4. So 1.4 would be somewhere here. And then let's do the same thing on that side. 1.4 is somewhere here. Okay, so we have some points that we can connect. So this side would tend like this. The next piece will kind of curve between these points and do that. And then this side will do something like that. Okay, so this is a cube root of a polynomial. Lastly, I don't want you to forget how transformations affect a graph. So this particular example, let's do some rough work before we do the full graph. So we have a polynomial inside of an absolute value. The polynomial inside of absolute value could be factored, so it's a quadratic. So this quadratic has zeros at -2 and +2. When we take absolute value of this, then we reflect anything that was negative to be higher. And then finally, if we're adding a 2 at the end, we're just shifting everything up by wherever 2 happens to be. So final graph is a graph like this that's shifted. These values right here is at 2. All right, so don't forget transformations as you're doing these. I hope this helps.